Okay, so we are now going to get formally started with the course. But before we do any fluid mechanics, we will actually do an exercise through some of the tools that helps us look at equations in fluid mechanics. So what we are looking at in this course is fluid mechanics, which is a branch or which is a part of a broader field known as continuum mechanics. And typically when you are working in problems where you are thinking of deformation, stresses, strain and respective response of the system to that, it's more compact and convenient to use what we will learn today during the lecture and probably also going to the next lecture, which will be on tensors. So this is not going to be a complete description of what tensors are. We can't do justice in a few lectures on what tensors actually would be. But whatever bare minimum that we need in order to get through learning how to work with equations of motion, that's something which we will work towards. So the starting point is are things which we are already familiar with regarding vectors. So if I were to say that I have to define a particular vector, so I am going to use this squiggly notation below in place of putting an arrow on top to denote a vector. So any vector, I can write a representation in a coordinate system, and I am going to choose a Cartesian coordinate system. So E1, E2, E3 are basically the coordinate axes that I have. You could think of them as X, Y, Z. And the representation of the vector in terms of these components would be A1, A2, A3. So now if I want to actually do operations with this vector, so there are various operations that you are familiar with in terms of we would effectively look at things which you already know in terms of that if I have another vector, let's say B, what would be the dot product of A and B, or what would be the cross product of A with B. So these are quantities which you already know. There is nothing particularly new here, but we will see that is there a different way of making all of this in a more compact manner. So for instance, to start with, since we are dealing with the coordinate system as shown here, E1, E2, E3 being the unit vectors. So the unit vectors are vectors which will have by definition of unit length, which means if I were to, so E1 is also a vector, so ideally I should put a squiggly sign below these also, but we will understand that when I write E1, E2, E3, they are actually vectors of unit length along the axis 1, 2 and 3. So they have, so this should be 1, so they have unit length, and the direction basically denotes the direction of the axis. Now if I just look at these unit vectors, if I do a E1 dot E1, which is what I already have written down, it would be unity. That's the dot product of the vector, unit vector along 1 with itself. If I do E2 dot E2, similarly, I will get unity, and E3 dot E3, I will also get unity. But if I take a dot product of E1 with the other components, which would be E2, it will be 0. Similarly with E3, it would also be 0, and subsequently E2 dotted with E3 would also be 0. So they are all orthogonal. We have an orthogonal coordinate system here. So since we have an orthogonal coordinate system, the unit vectors are orthogonal to each other, which gives us this what is almost a trivial relationship between these unit vectors. Now can we write this, so we have written here 5 relations. So can we write this in a more compact form? Instead of actually explicitly writing every time the relation that we have for the dot products, can we write this in a more compact form? So what I will do here, I will write E1, the ith component, Ej is delta Ij. So what this tells me is that now I have this quantity delta Ij, which will pick a value 1 if I is equal to j, and will pick a value 0 when I is not equal to j. Okay, so I am taking a dot product of these unit vectors along the prescribed direction, and I am writing it in one single notation here. So automatically now I see that I don't need to write those 6 relations explicitly, rather I have this relation where I am using this shorthand version of what would be the respective dot product. Now similarly, if I were to write down the cross product, I can write a cross product of the vector E1 with itself, and we know that this answer would be 0. Similarly, I can write down a cross product of E2 with itself, and the answer would also be 0. The same holds true for E3, and the non-zero answers that I would start getting is when they are perpendicular to each other. So when they are perpendicular to each other, then E1 cross product with E2 would actually give me E3. So the unit vector along 1, its cross product with unit vector along 2 gives me E3. And something which you can just keep a little bit of a note now, we will revisit this towards the end of this section, is when I write E1 cross E2 as E3, I am implicitly making an assumption regarding the handedness. So I am actually saying that E1 cross E2 is E3 with a plus sign, not minus E3, which means I am choosing a certain handedness regarding the coordinate system. So we will revisit this almost towards the end of this particular section, but a point to just keep in mind. Similarly, E2 cross E3 is going to be E1, and E3 cross E1 will be E2. And by knowing what you know about cross product, you know that if you were to do E1 cross E3, that would be minus E2, and you could work this out for all the cases. So this introduces us to another shorthand notation which you are going to use, what is known as the permutation symbol. So this object, the permutation symbol, I have basically given it 3 labels, I, j and k. What this tells us is that if all these 3 indices were equal, or if 2 of the indices were equal, this would pick up a value of 0. So if either I equals j, j equals k, I equals k, or I, j equals k. So if any of these cases were to occur, that I, j, k, you at least had 2 of them being equal to each other, this would pick up a value that would be equal to 0. So this is where I, j, k individually are going to run over 1, 2, 3. So I can take a value 1, 2 or 3, similarly for j, similarly for k. So now you can see E111, E122, E331, E212, and then so on, for all those combinations would all be 0. Now if I, j, k were in a cyclic order, what does cyclic order mean? So what I have written down above, 1, 2, 3, 2, 3, 1 or 3, 1, 2. So if you have these in cyclic order, the permutation symbol picks up a value of plus 1. And if it was in the anticyclic order, which means 1, 3, 2, 2, 1, 3, 3, 2, 1, then it should pick up a value of minus 1. So I have used this shorthand, and you might now ask that why am I doing this shorthand notation? Because the shorthand notation will now give me a handle of how I do my cross product. So if I am now writing the unit vector in the ith direction, I am basically going to take a cross product with the unit vector in the jth direction. This will be related to my permutation symbol that I have, and I get in terms of k. So let's check if this is indeed correct. So if I choose I and j as 1, both I and j I choose as 1. So, E1, E1. So, I have epsilon I 1 1 k E k. Now, but then there is k that you see here that is repeating. So, what you will actually have here is a summation over all possible values of k, which means this object is epsilon 1 1 1 E1, epsilon 1 1 2 E2, epsilon 1 1 3 E3. And each of these quantities are going to be 0. Why so? Because you can see that the permutation symbol has indices which are the same in all the 3 cases. Now, let us try the next case, which is if I take E1 cross with E2, which is to say that I am going to have epsilon 1 2 k E k. So, it is summed over all k's. So, I will write this explicitly 1 2 1 E1, epsilon 1 2 2 E2, epsilon 1 2 3 E3. Now, let us check these permutation symbols. The first two, there are indices which are repeating. In the first one, 1 and 1 repeats, second one, 2 repeats. So, effectively these are all going to be 0. And in the third one, you have 1 to epsilon 1 2 3, and if I go back to what we learnt in the permutation symbol definition, epsilon 1 2 3 would be plus 1. So, I get plus E3. If you repeat this with E2 cross E1, then I will have epsilon 2 1 1 E1. I am jumping directly to the expansion, 2 1 2 E2, epsilon 2 1 3 E3. And we see once again the first two vanish off, and what I am left with is epsilon 2 1 3, which if we recall from our definition of permutation symbol is minus 1. So, what we have done is nothing new in terms of just revisiting dot products and cross products, but what we have done in the process, we have come across two new symbols. So, there is the first one which has two what we are going to call as indices. So, I and j, they are indices. This is going to take a value of plus 1 if I is equal to j, and will take a value of 0 if I is not equal to j. So, this is known as the Kronecker delta. And the other one that we learned was epsilon ijk, which is what is known as the permutation symbol, that takes a value of plus 1, minus 1 and 0. So, plus 1 if it is cyclic and order, minus 1 if it is anticyclic order, and 0 if you have them repeat, if at least two indices were to repeat. So, this is known as the permutation symbol, or later we will call them as the permutation tensor. So, this is what we have now as a tool in order to do calculations. So, the next part that we are going to do here is with this tool, the last bit of this calculation is when I am writing this as E1 cross E2 as summation over E12 k epsilon 12 k Ek. We are doing a summation over all values of k. So, it is actually k running from 1 to 3. So, there are 3 dimensions that we are looking at. So, k goes from 1 to 3. Now, every time we are not going to carry forward this summation. So, what we will instead do is we will remove the summation symbol, and whenever you see these indices repeating, it will imply summation over that particular index. So, I am not going to explicitly write out the summation sign every time. Whenever you see these indices are actually present twice, that implies that we are going to do a summation. So, we will now let's do a few of the standard vector relations that you are aware of. So, A dot B. Now, what is A dot B? A dot B I can write as AI EI. This means it's A1 E1 plus A2 E2 plus A3 E3. This is now dotted with BJ EJ. So, you notice here that the index that I chose for B, I chose it different than A, because this here I would run from 1 to 3. This J also runs from 1 to 3, but it can take any sequence of 1 to 3, and this can take independent of it. So, the two summations are independent of each other. So, this one would also be B1 E1 plus B2 E2 plus B3 E3. So, let us now do the dot product. So, I will have I equals 1 to 3, J equals 1 to 3, AI BJ EI dot EJ. So, EI, to remind again, is the unit vector in the ith direction, EJ is the unit vector along the jth direction. And we just saw that when we do this, this is going to take up a value which will be, so EI dot EJ would obviously be non-zero if both are the same. If they are different, I am basically going to get them to be 0. So, I can write it as delta Ij. So, EI dot Ej gives me delta Ij. So, now I have the summation of A dot B written as AI Bj delta Ij. But then I can see that delta Ij is this object which has these two indices. Only if those indices were the same would I get a non-zero value, which is plus 1. If the indices were not the same, I would get 0, which means in the summation you can write this out explicitly, but in the summation the only non-zero values would appear when J for B and I for A, the ith component of A and the jth component of V, they are basically the same components or the same directional components of the individual vectors, which means this is going to be AI BI summed over I equals 1 to 3. So, what I have done here, I have taken Bj delta Ij over all j, and that I have written as Bi. You could have also done it the other way around. You could have also written this as summation over Ai delta Ij, in which case it would be Aj. So, this could also be written as j equals 1 to 3 Aj Bj. There is no difference. There isn't any difference for the reason being that you have what would be a dummy index. So, the indices are repeating and you run over that same index. So, now as I said earlier that I am going to actually drop this summation sign and I am going to just write it as Ai Bi. And this dropping this summation sign is what is we are doing is Einstein's notation, that whenever you have repeated index, it gets clumsy. When you are going to basically do this summed over several indices and in future, it becomes more convenient that you are agreeing to this notation. So, it's a convention that we are agreeing to. The convention basically being that whenever you have repeated index, is going to be summed over. So, AI Bi, we all are going to agree means A1 B1 plus A1 B1 plus A2 B2 plus A3 B3. and that would be exactly the same if you wrote it as AK, BK. There is nothing sacred about calling them as I, J or K. The moment it is repeated, you are free to choose whatever index that you have. So, this is doing what you know, but using a slightly different language of how we are putting it across. Now, let us do a cross product. So, A cross B. So, A cross B is going back to what we had, it is AI EI cross product with BJ EJ. This runs over all I, this runs over all j. So, I will take the two summations outside, and what I have now is AI EI cross product with BJ EJ. AI and BJ are the components. So, they are the components of that particular vector. So, I am going to just write them as AI BJ, and the vectors for which I have to do this cross product is EI cross EJ. So, we have a unit vector along the ith direction and its cross product with a unit vector along the jth direction. And then we have seen from the relation that we have for the unit vector that when I take the cross product of a unit vector along the ith and the jth direction, the resulting quantity that I will have is going to be AI BJ epsilon I j k E k. So, we have done this by substitution. So, we have said that let us take I as 1, j as 2, and eventually the answer that you are going to get is the cross product is E3. If you were to take E1 and E1, I being 1 and j being 1, the answer would be 0. So, now I have this EIJK that is actually there. So, you have this relation now which is summed over I, j, and I have epsilon IJK AI BJ EK. So, now if you see that you have these repeated indices that are actually appearing in the problem. So, this is basically the direction in which the final vector points. The repeated indices that I have are over I and j here. So, what I will write is that the kth component of the cross product is epsilon IJK AI BJ. And you can verify this how you have already done this before, where you know how to write down a cross product, that if you were to write this in a determinant kind of a form, the individual component that you are actually going to get would involve taking the corresponding component by component multiplication of it. So, this is exactly what you are going to get by verifying it. So, this is what you have now as a notation for writing your dot and cross products. So, we have A dot B as AI BI, which is a scalar, whereas A cross B is a vector, and if I want to now write its ith component, then the ith component will be epsilon IJK AJ BK. So, the ith component of the cross product would actually involve having the permutation symbol in doing this in terms of the individual component. So, there is one more vector which we are going to frequently encounter when doing calculation, and that particular vector is the del operator, and the del operator in a Cartesian coordinate system you can write in this particular form. Each of these, again I am not using the vector sign for the unit vectors always, but each of these are components that are along the 1 direction, 2 direction and 3 direction. So, now if I do something that we will see So let's take a vector field V which has component V1, V2, V3, and if I take a dot product, which is in vector calculus known as a divergence, then I will have E1, I'll use indices now, summed over all I, just like your dot product that you did, J, Vj, Ej. So that gives me, if I take my I and j summation outside, I have Ei dou xj Vj Ej. So the derivative along the, sorry, this would be still it's in the ith direction. So this is a derivative along the ith direction which is acting on the vector whose components are written in the form of indices Vj, Ej. Now we are dealing with a Cartesian coordinate system. Now why I am specifying Cartesian coordinate system? So if it's a Cartesian coordinate system, the unit vector E1, E2 and E3, they are obviously unit by definition, which means they have unit length, but they are also constants in direction. They don't change their direction. The direction of your unit vector along the 1 axis, along the 2 axis, along the 3 axis in Cartesian coordinate system don't change. So this is a point that becomes important when you move to a coordinate system that is not Cartesian. If you were to do a curvilinear coordinate system, in which case the unit vector will not necessarily have the same direction. It will always be unit length, it will not be the same direction. So when you are doing the derivative, you have to be a bit careful. But we are restricting ourselves to Cartesian coordinate system here. So in which case Ej, the unit vector, is a constant truly in magnitude as well as direction. So I am going to take it outside the derivative, and now I have Ei dotted with Ej, and we know that is a delta Ej. And then using the property of the Kronecker delta, I have this as dou Vi dou Xi, which you are probably you have seen this in the definition of a divergence in the past as dou V1 dou X1, dou V2 dou X2, dou V3 dou X3. So the divergence can be written in a compact manner as dou Xi of Vi. In the same way, the other operation which you are probably seen is taking a cross product with the del operator, which is known as a curl. So when you do a curl, you proceed in fairly similar manner as what you did for the divergence, and what you end up with is a cross product of the unit vector so when you have the cross product of this, going back to what we have written down before, this will be, if as you can see I and j are the ones indices which are repeating, so I will have k Ij dou Vj dou Xi. So k here is what we call as the free index. So the free index of the curl, or rather the curl of a vector will be a vector. So if I am interested in a particular component of that vector, so epsilon k Ij dou Vj dou Xi. Once again, as you see that the notation the indices I and j are repeated, so you are going to repeat over those values. If you were to write this as you would prefer to write is this the ith index of the curl, then it would be I, and then you are free to choose what you want as a repeated index. So you could call this as mn, and then the last index appears for the component of the vector, and the second index is the derivative direction. So just to make this point that the repeated indices, there is nothing sacred about what you choose as your letters for your repeated indices. You can choose whatever you want. Just don't mix up your free and repeated index. So here, because you are dealing with a vector, you have a free index, which is the direction of the final answer. Curl of a vector will be a vector itself, and there is a direction associated with it. But when you are finally writing down the curl, you will have these repeated indices. So don't choose a repeated index letter which is the same as the free index. So the point I am saying is, don't do something of this sort, because this is an incorrect notation. Because you have mixed up a free index and you have also chosen a repeated index, you are going to make an error by doing this. So that's the part which you need to pay a little attention to. So now we have some of the tools that are necessary in order to actually go ahead and see. So far everything seemed more like we are introducing a more compact notation of doing vector calculations. Whatever you are familiar with, either in doing straightforward vector dot products or cross products, or doing vector calculus, some of those things are things which you are able to see and do here. Now we will take this forward a little bit more and try to generalize how we are going to look at these objects. So if I have a coordinate system that I have drawn, so if I have 1 or 1, 2 as my coordinate system, then I will now say that let me rotate this coordinate system. So if I rotate this particular coordinate system by some angle. Now if I am trying to write down that my initial, so I have, let's say, a vector, I'll choose the vector as A, which we have been doing so far, as A1 E1 plus A2 E2 plus A3 E3. So there is some vector that I have here, which I have marked using the original coordinate system, which I call as the old coordinate system. So the unprimed variable is my old coordinate system, and the prime variable is my new coordinate system. So now you have this vector. Now if I were to transform, the transformation of this particular vector is now not going to change the vector. What it will change would be the components of the vector. The components of the vector are going to change. So if I know the angle, so I will denote angle which is 1, 1. So what is 1, 1? Alpha 1, 1 is the angle between the old one direction with the new 1 prime direction. Similarly, if I write this as alpha 1, 2, it would be the direction angle that is between the old 1 direction with the new 2 direction. So in this manner, you can basically define all the angles that would actually be there. So in which case, now I can say that if I have the vector have components A1 prime, E1 prime, A2 prime, E2 prime, A3 prime, E3 prime. So, I have just done a rotation of coordinate system. I am showing it only for the two axes here, but you can imagine that there is an arbitrary three-dimensional rotation of the coordinate system. So, when you have an arbitrary three-dimensional rotation of the coordinate system, you will in general have angles which I can write as alpha ij, which means each axis is rotated, and now you can find the angle that is subtended by the new jth axis with the old ith axis. So, with this I can write my components after doing the transformation. So, this is just a coordinate transformation, would be a1 cosine alpha 1 1, a2 cosine alpha 2 1, a3 cosine alpha 3 1. This is just by doing a coordinate transformation. So, whatever was your previous coordinate system, so previously this was your a1. Now, this is your a1 prime. You are representing the same vector in a new coordinate system. So, the component that you have along the new coordinate system will obviously be different from the previous component that was there along the previous one coordinate system, and it will involve combination just by virtue of this coordinate transformation. So, now if I use an index notation, what should this be? So, again if I start with the summation basically tells me this is some ak cosine alpha k 1, which is a1 prime, and using Einstein notation that we have just adopted, I will write this as ak, and instead of writing the cosine, I am just going to write it with a new quantity, which is an object C which has I and j as its indices, which is cosine of alpha ij. So, a1 prime is now equal to ak ck1, and ck1 are basically my direction cosines that I have. So, you can think of this now as a matrix whose elements are going to be the direction cosine. So, it will have cosine alpha 1 1, cosine alpha 1 2, cosine alpha 1 3, and so on. It is going to fill up this particular matrix. So, you have now a representation. So, we have used few things here. We have used indices to represent quantities. We have also used the Einstein notation, because you can see what would have actually been a summation here of k running from 1 to 3. I am not writing that summation. I have dropped that summation, and so by dropping that summation, I am just using a shorthand of saying that if I have any ith component, the ith component can be written as the following. So, ak cki. So, this is just saying that a vector in a transformed, or rather a rotated coordinate system, will have its component transforming by this particular rule. So, cki that you have here basically represents your rotation matrix. So, that takes the components of your previous coordinate system, the components in the previous coordinate system, and gives you the components in the new rotated coordinate system. So, if you were to write this in instead of indices, what will this appear like? So, this is a vector. Now, you can see this is A dotted with what is an object that has two indices, and I was writing it as a matrix, which means that there are 3 rows here and 3 columns that you would have. So, I have written it with these 2 double squiggly signs here to indicate that you have 2 indices to describe this particular quantity. The other way to write this would be C transpose dotted with A, because as you can see, the ijth component of this is Cij, but the ijth component of C transpose would basically be Cji. So, you have now the relation that we have drawn in terms of how this vector basically transforms. So, we have a relation for vector transformation under coordinate transformation, and since this is a rotation matrix that we are talking about, there is a property of this is this particular matrix, the rotation matrix that we have, this transformation is a orthogonal transformation. So, what orthogonal transformation, if you have done this in matrices, what it tells us is that the inverse of the matrix is its transpose, which means if you were to find the determinant of C times C transpose, that is going to be the determinant of the identity matrix, and the determinant of the identity matrix is 1. Now, the determinant of these two matrices can be written as determinant of C multiplied by determinant of C transpose is equal to 1, the determinant being the same as that for the transpose. So, I have determinant of C square is equal to 1. So, for this orthogonal transformation that we are doing, for the orthogonal transformation we have the determinant being plus 1 or minus 1. What we are doing here for rotation, we are dealing with orthogonal transformations which have a determinant of positive unity. And then again, recalling what we were earlier discussing regarding handedness, we will revisit what happens when it is minus 1. So, for now just focus on the transformation which is the rotational transformation. So, I rotate my coordinate system and I have the element of this particular vector rotating in this particular manner. Now, while doing this, we encountered this object which is in a manner of or analogy with matrices is something that has 9 elements, 3 rows, 3 columns. There are 2 independent indices that are associated with it. So, now you could ask the question that if I have the same transformation being applied to an object which has 2 such indices. So, I do the same coordinate transformation of rotation, how will that quote unquote matrix, I am using the analogy with matrix interchangeably, how will this quote unquote matrix actually transform under the coordinate transformation that we are looking at. So, if I denote this in index notation, so first I will use what we call as the bold-face notation. So, bold-face notation is what you will typically see in a textbook, where vectors and objects which have higher indices, they are denoted with a bold typeface. So, if I use that bold notation, it will transform using the following rule. So, C basically again being the orthogonal transformation that you have. So, you have rotated your coordinate system and you have the object which has these 2 indices transforming based on this rule. So, if you write this out explicitly, so if you say that the transformed object, if I am interested in its I and jth component, so you know, let us do this carefully. So, this would be for the transpose I k, then k, it is a dot product. So, every time we have a dot product, we have learned that a dot product effectively can be written in this manner, and the next one will be m j. So, what I am effectively doing here is, if you go back to how you understand matrix multiplication, if I take a dot product of two matrices, then the dot product would be A I K B K J summed over all the values of K. And I am not writing the K explicitly, so it is I K B K J. So, if there is a product of two matrices, then the ijth element, the ith row, the jth column of the new matrix or the product matrix is Aik multiplied by Bkj. And you can write this, if you want, you can write this explicitly. So, you are basically doing the column of I multiplying with the row elements of B, and that is how you create the matrix product. The same exact same thing I am doing here. So, there are two matrix multiplications that are happening out here. Now, the ikth of C is going to be Ki of, or ikth of C transpose will be Ki of C Tkm Cm J. So, T prime Ij will transform in this following manner. And this quantity, which is now an extension that we are seeing beyond what we have learned for vector, is a second order tensor. The second order basically comes from the fact that we have these two indices that are there. So, it is of dimension 3. So, we are doing in 3 dimension, but there are two indices. So, it is a second order tensor in 3 dimension, which is why it will have the number of elements it will have will be 3 square, which is 9. That is again some aspect that we just said, that if there is a 3 cross 3 matrix, you will have 9 elements. So, a second order tensor is an object which transforms under this rule. So, just the way you saw it for a vector, that when you did this for a vector, you had A prime of I was C J I A J. This is how a vector actually transformed. And in the same way, now you have a relation of how an object that has more degrees or more order than what you have in a vector. So, the vector you can now generalize and use the same language and call as a tensor that is of order 1. So, first order tensor would be a vector, and if you continue going below, a 0th order tensor is what we have always been calling with a name known as scalar. So, this is trying to put everything together in one single umbrella. So, I'll stop here today. We will start to see in next class what do we, why are we doing all of this, like what is the connection of doing this with fluid mechanics. So, we are trying to introduce these objects because this is going to be probably one of the first instances where you are going to see things that are second order tensors. So, previously you would have dealt with objects which are vectors and scalars. So, there was no need for trying to create this one single family of objects and how they behave in this mathematical manner. So, this one single mathematical representation becomes important because in fluid mechanics you are going to see objects that are second order tensors, and we will also see in the next lecture that there can be third order tensors, fourth order tensors, and they are going to appear in the consequence of when we write down momentum equations. So, that is why getting this kind of a universal framework is important. Okay. So, I will stop here and I will take questions. Yes. Yes.
We are doing the rotation transformation for in a 2-axis coordinate system.
I am showing 2 axes because it is easier to show, but you are doing actually a full 3-dimensional rotation. So, you have the 2 axes rotating, and then you can also have a rotation. So, right now what the picture shows, it shows a rotation about an axis coming out of the plane of the board, I mean of the sheet, right. So, there is a rotation which is a planar rotation, and then you can do another rotation where you do a rotation out of that particular plane. So, you can have rotation which is a full 3-dimensional rotation. In the 2D problem, there is only one angle to track. because finally the rotated coordinate system should also be orthogonal, so you only have a single angle to track about in 2D. But when you are doing in a three-dimensional sense, you can have rotation about all the three axes.